It's a window
Okay.
for this.
Okay, so today I'm just going to do like a little mini intro to the fundamental theorem of line integrals and just review some things we've already talked about. And then tomorrow I'll talk more in depth about line integrals. So fundamental theorem of line integrals. Okay, which I'm going to call Vitoli for short. What's going on here? Okay. Okay. All right. So let's quickly go over things we already know. So about line integral, a line integral on a vector field. So if C is some parameterized curve R of t with t from A to B and F is a vector field defined on C, or defined on some domain that includes C and therefore is defined on C. Then we know that the line integral of a vector, the line integral on a vector field, the integral along C of f dot dr is the integral from A to B of f of r of t dot r prime of t dt. Okay. And this integral does not depend on the parameterization of C as long as you're going in the same direction. So if you switch directions, so we call that the integral over negative C of f dot dr, then the sign of the integral switches. So that would be negative integral of C of f dot dr. Okay, but other than that, it does not depend on the parameterization. And then also, way back in the beginning of chapter 6, we talked about 16. Sorry, we talked about that F is a conservative vector field if f is the gradient of some function little f. And I will review the process for sort of the mechanical process for proving that. Okay, so that's what you already know. So the fundamental theorem of line integrals says that if why aren't you working? If the vector field f is the gradient of little f, which means that's another way of saying if f is a conservative vector field and C is a parameterized curve R of t from A to B then the line integrals over C of f dot dr equals, well, because we just said vector field f is conservative, I can write vector field f as gradient little f dot dr, and that will equal the little f of b minus little f of a. I'll prove it in a second, but let me just kind of explain what's going on here. So we have some curve. I mean, I'm doing this in 2 dimensions now, but it could be in any number of dimensions. C, and let's say C is oriented in that direction. B would be R of B, and A would be R of A. Okay. And if you look at this rule here, this is actually very similar to the fundamental theorem of calculus, right? So for the fundamental theorem of calculus, we would say that the integral from A to B of, let's say, take a function g, a function of x, call it g, g dx, the derivative of g with respect to x, dx, would equal g of b minus g of a, right? So this is analogous to that. In the fundamental theorem of calculus, to integrate the derivative of a function over an interval from a to b, you just evaluate the original function at the endpoints and subtract. And then here in the fundamental theorem of line integrals, you're integrating the gradient of a function along a curve, which is a form of a derivative, right? And so you integrate the original function at the 2 endpoints and subtract. Instead of having a derivative with respect to x, like you do in the fundamental theorem of calculus, you instead have the gradient, but otherwise it's completely analogous. And so a corollary to this, so would be that if f is conservative, then the line integral over C of a vector field depends only on the endpoints A and B. And not on the path C. Okay. If you remember a couple days ago in the second lecture I did about integrals of vector fields, line integrals of vector fields, I did 2 examples of how to integrate the same vector field along 2 different curves with the same endpoints, and I got 2 different answers. So it was like one of the integrals I got, the answer was 2, and then the second time I did the integration, the answer was 11/6. So because those 2 values are different, that could not be a conservative vector field. Because if you have a conservative vector field, you'll get the same answer no matter what curve you choose between 2 given endpoints. Okay, any questions so far? All right, so I'm just going to do one quick example to review the process of mechanically proving that a function is a gradient. Sorry, a vector field is a gradient of some function f, which remember we refer to as a potential. So the mechanical process for finding a potential. Okay, so we are going to, example. Okay, calculate the line integral over the vector field f. if f equals 2xyz plus e to the x plus z, x squared z, sorry, x squared, yeah, that's right, x squared z, and then x squared y plus e to the x plus z. All right, and then we're going to say that C is a curve from 1 to 0 to 105. So in general, only knowing the vector field F and the endpoints of C might not be enough information to evaluate an integral, because generally the integral of a vector field along a curve depends on the path from point A to point B, which we're not given here. You're just given endpoints. But if F is conservative, then it does not. Okay, so again, I'm just going to review the mechanics of the mechanical procedure for finding a potential F for gradient F. So the question we're asking here is vector field F gradient F for some potential function little f? Okay, so you so basically the idea here is that I'm going to integrate area variables one by one to figure out what little f is. Obviously, you could just look at this one and probably figure it out just pretty easily from using just visually. But okay, well, how am I going to do this? So I pick one of the derivatives, right? Remember, this is partial x, partial y, partial z. I'll just start with partial x, but you can start with any one of them. So partial x is 2xyz plus e to the x plus z. So that means that f of x, y, z must be the integral from 0 to x of 2tyz plus e to the t plus z dt plus, well, what goes here? What else could be in the function? Okay, I'll say it's g, some function that includes y's and z's, right? G of yz. Because if you have a function that includes y's and z's, when you take the derivative with respect to x, that becomes 0. All right, so now I'm going to integrate that. So f equals, that's going to be t squared yz plus e to the t plus z from 0 to x plus g of yz, which now I'm going to plug in my x. I get x squared yz plus e to the x plus z. And then I'm going to get 0 minus 0, and I'm going to get minus e to the z, minus e to the z, and then plus g of y z. Okay, so now I'm going to go on to the second partial derivative. So now I'm going on to this one up here. Partial y is x squared z. So now I'm going to say, okay, the derivative of f with respect to y is x squared z plus well, that's going to be a 0 and a 0 for this and this. And then I'm going to have partial G, partial Y. But we already know that from our original vector field that partial Y should equal X squared Z. So again, I got this from up here. That's what partial Y needs to equal. Well, that means that partial Y or partial G partial Y equals 0, which means now if you integrate that, you're going to get that G of YZ equals C plus, well, actually, let me just rewrite that. That's going to equal only some function of Z. You could, yeah. Oops. I'll call this H of Z. Okay, any questions so far? All right, now I'm going to put this right back in here because, and I'll just say this is a constant in this context. Constant for partial G, partial Y. All right, so now I'm going back, and this is the equation that I have right here. So now I have that F is X squared YZ plus E to the X plus Z minus E to the Z plus H of Z. And now I'm on my last partial derivative. So now I'm on partial Z. So I'm going to take the derivative with respect to Z now. So partial F partial Z is going to equal X squared Y plus E to the X plus Z minus E to the Z plus H prime of Z. And that must equal the given partial derivative with respect to Z, which is X squared Z plus E to the X plus Z. So again, here, that's coming from here, okay? And so I get the X squared Z's are gonna cancel, the E to the X plus Z's are gonna cancel, and I wind up with H prime of Z equals E to the negative Z. That's really my last step. Oh, sorry. No, that's not my last step. So therefore, H of Z is, oh, I made a mistake somewhere. What is it? Did I?
Is it E to the negative Z or just E to the Z?
Oh, E to the Z. Thank you. That's my mistake.
Yeah.
There we go. Right there. Yeah. I was like, this is not going to work. So we have a problem. Okay. Thanks. This is E to the Z. And therefore, H of Z is E to the Z. Okay. Now it's going to work. Okay, great. So this goes back in there. Oh, sorry. What am I missing there? I'm missing a plus C. There could be a plus C there, right? There's always an infinite number of potentials if there's a potential. Okay, so lastly, I get F of X, Y, Z is X squared YZ plus E to the X plus Z. And these two are going to cancel each other out because you have a minus E to the Z plus E to the Z. So this is my potential. So there exists an F such that gradient F equals the vector field F. Therefore, F is conservative, now I'm going to need to go on to the next page here. And so since if F is conservative, then the line integral over C of F dot dr equals F of, what are my points here? F of F of B. This is actually a very common mistake. Make sure you put B in here. 105 would be point B minus F of 120.
Wait, are you gonna upload
Okay.
this to somewhere?
If Samir is successfully recording it.
Okay.
Were you not here at the beginning of the lecture?
Or I was, but people in the Discord are banking on it being recorded.
Well, they should have come to class.
They should have.
Okay, so what is F? F, we just figured out was, okay, x squared y z plus e to the x plus z plus c. Okay, so I mean, you don't need the plus c because you just need any potential, but I'm just writing it there. F of 105 is 0 plus e to the 6th, and then F of 120 is 0 plus e to the 0. No, wait, hold on, 1, e to the 1. So then the line integral over C of F dot dr equals e to the 6th minus e. Ta-da. Okay, question so far? Okay, I'm just going to do one last thing for today, and then I will do more, like sort of the more important details about the fundamental theorem of line integrals tomorrow. Oh, not tomorrow. Not allowed to give you a lecture tomorrow. I might just post. Do you want me to do it live, or do you want me to post it? Or I can do it Monday.
I'm pretty indifferent. Both are fine.
Yeah.
Okay.
Wait, I have a question.
Okay.
If you're subtracting plus c's, then can't you still end up with a plus c?
What?
Because you don't
It would
like
be,
know.
it's e to the 6th plus c minus e plus c.
But would those plus c's necessarily have
They're
to
the
be
same
the same
c
thing?
because they're both.
Yeah.
Oh,
Yes, because they're.
got you. Yeah. Okay.
Yeah. Good?
Yeah.
Okay. Last thing I'm going to do is proof. Nice and easy of the fundamental theorem of line integrals. Okay. So, so again, what am I proving? So I'm proving that if vector field f equals gradient f for some function little f, and if C is a curve R of t from A to B, then the line integral over C of F dot dr is F of B minus F of A. So they're sitting on the Discord chatting, but they don't want to listen to a lecture. Okay, anyways, whatever. All right, proof. So you're going to choose a parameterization of C as the vector valued function R of t, where t goes from A to B. Given R of A, it would be point A, and R of B would be point B. So we've got something like, this is X, Y. Again, I'm illustrating a two-dimensional case, but this does apply in n dimensions. So, and then we've got our parameterized interval, where we have R of t mapping from our interval to our curve C. Okay, before I sort of do the proof, I'll just, one more thing that from before that you need to know in order to understand the proof is just remember the vector version of the chain rule. And that says that the derivative with respect to t of f of r of t, 1, 2, 3, okay, equals the gradient of f of r of t dot r prime of t. And of course, this is the vector form, right? In components, that would be d dt of f of x of t y of t equals partial f partial x x of t of x of t y of t x prime of t plus partial f partial y x of t y of t y prime of t. Okay, so okay, the proof. So we have all of this as our givens. So then, by the fundamental theorem of calculus, we'll use that in here. Okay, the line integral over C of f dot dr equals the integral from A to B of f of r of t dot r prime of t. But we made the assumption that that the vector field f was conservative and therefore is the gradient of some function little f. So I can replace that with the integral from A to B of gradient f of r of t plus r prime of t. Oh, I forgot a dt here, dt. But going backwards from the vector version of the chain rule, that I can rewrite as the integral from A to B of the derivative with respect to t of f of r of t dt. But by the fundamental theorem of calculus, the the integral of a derivative will just give me the original function. So if I take the derivative, then integrate, I'm going to get f back. So I can write this as f evaluated at r of b minus f evaluated at r of a. And then, of course, I designated at the beginning that r of b is point B and r of a is point A. So therefore, I proved that if f is conservative, then the line integral over C of f dot dr equals f of b minus f of a. Ta-da! I think I'm going to stop there. There's a lot more to talk about relating to conservative vector fields and the fundamental theorem, but I'm just going to stop there. I'm only going to assign 3 problems, and I'm going to have them do them what I would consider the long way, which is I want you to practice this process of mechanically finding a potential. Okay, just 3 problems, and Monday we'll talk about some shortcuts for that. All right, questions on anything or questions on the homework that you, Samir, you could probably stop now.